Okay, so let's first go through the stuff what I have changed on the OMA. So first of all, on the documents, I added the videos for lecture and also the exercise tutorial. And basically, what else? And then, oh yes, I added some extra information, other implementations. If you open that one, it actually takes you into a little bit different DSP implementation. It's a DSP problem solving, which is mostly taught as Erasmus exchange course in Frankfurt University of Applied Sciences and Bonn-Rhein-Sieg University of Applied Sciences. And practically, it has about the same contents. However, there are some history about videos, a little bit different point of view, and also a little bit different explanations, since those are mostly done in classroom. And on classroom, there is a nice whiteboard or blackboard. And there are actually some explanations on video, and also some of that stuff is also explained in whiteboard. So that's some extra material if you don't get everything from these brief notes and the books I have mentioned. But anyways, those are at your disposal. Use as you wish. Today's topic is the part 2, systems. And basically system fundamentals. Let me put that one on full screen. It looks a little bit better. Okay. Last time we have signal fundamentals, how to produce a sampled sinusoid, for example, or any other function. All of the basic signals like the unit impulse and unit step function in digital domain. And then basically just fundamental stuff. Today, this is fundamentals of digital systems. And first of all, what kind of operations we actually have on digital signal processing. These are the basic or fundamental DSP operations. Only 4 of them, which sounds pretty good. And actually, the first 3 are needed in any linear system. So there are just addition, scaling, and delay for linear systems. And then if you are dealing with also other systems, then you basically also sometimes need multiply the signals. Signal multiply meaning the mixing the signals. The same as in radio technology, you have the modulation. So one of these signals would be the modulating sinusoid, and another one would be the signal which is sent out. Okay, addition is simply adding two values, and the block diagrams. In block diagram, it shows like a circle with a plus at the middle of circle with the sigma sign on the middle. In mathematics, well, it's just either plus or sum of several values, then it's the big sigma. Scaling meaning multiplying by a scalar. So a constant value multiplies a signal. So difference from the multiply operation. Scaling is actually a linear operation, but multiply is not linear. Block diagram symbol is simply a amplification symbol, so a triangle with the amplification or scaling term at the middle. You are familiar with that already. Then third one operator is the delay by k number of samples. In mathematics, it looks like x of n minus k, where the k is the number of delays. And the block diagram symbol, it's either that k times d, and k here can be, well, any constant number. For example, if you have a single delay, then simply this block diagram symbol is simple d, 1 times d. Then the other one here is the z minus k. Sometimes the delay on the block diagram is shown like that. By the way, I have a monitoring screen next to me, and at least that one seems to do some funny stuff like breaking out once in a while. If you have big problems on this stream, it might be due to the problems with Zoom connection. Okay, but anyway, so those three first block diagram and or operators are used in linear system. And then, of course, sometimes we need that signal multiply also. Okay, so those are the basic DSP operations. Quite simple. Properties. These are not about being a good or bad system. All of these are just, say, fundamental properties. One important property is the linearity of the system. So practically, it means that can we forecast what the system does by simply testing it with a simple test vector. So if it's not linear, then basically you have to deal with some statistical tools to characterize the system. But if it's a linear system, then you can actually formulate it with a explicit formula how the system works. And practically it means that the superposition applies, meaning if you have an input or sum of inputs, weighted sum of inputs, and you feed that one through the system, then basically it should be the same as the system individual signal fed into the system and track, well, effects of the sum. Sum of effect is equal to effects of sum. It's a little bit hard to explain here. Maybe I could use some annotation tools to see if I can do any better annotation than last time. Draw. Okay, let's see. Red. So this one basically means that if you have an input, you feed the input to a system. Now I'm still lousy on drawing like that. And actually, you first take the amplifier. It's so frustrating. So you have A multiplier A, and this is the system F. So that will be basically that part. Oops. if our signal is X1 here. Okay, so practically you would have two of these, X1 and X2. Like that. Go through the same system, and same system, and then maybe like that, right? That's amplification B for X2, same F, and drawing a circle here. Okay, good. Then we sum those output together. So actually, this one here would be, okay, the output part. The other way would be actually to have a, let's see, how does it work? No, it doesn't work at all. Sorry about that. I really miss pen and paper or whiteboard, real whiteboard, real blackboard. Maybe next time I will have a pen and paper and camera. Anyways, so practically you feed in the signal. Okay. Separately to a system, two signals, and then multiply. It's the same as taking the summed weighted inputs to the system separate. So that's what linearity is all about. The same actually as in the analog electronics. If you have a linear system, meaning no distortion, then basically you can analyze the system by feeding in a the step function from function generator, and then determining what is the system doing that way. Okay. Clear the drawings. There we go. Okay, the next one, causality. Causality means that the system does not react before there's an input, meaning it does not do any forecasting. A human being can actually forecast what is coming in future, or intelligent systems actually are expecting, and they can be very reactive by themselves or react before something happens. But in reality, say, that's not necessarily a good thing, since machines do mistakes, and they do bad mistakes, then people die. So causality, I would say it's a good property. A good digital signal processing system is causal. It does not act before there is input. But, well, that ain't true actually. If you're working with artificial intelligence and that kind of things, then causality is not necessarily a good thing anymore. Stability. Stability means that for bounded input results in bounded output. For example, on your electronics, if the system saturates, then it's not linear anymore, but it is stable. So analog electronics, meaning that if you saturate your amplifier, it has basically some limited input, and the output is also limited by the power supply voltage range. But in digital domain, you can quite easily generate a system which results into a some unlimited values, meaning infinite values or not a number values. So stability is quite important property. On analog domain, it means that you would have the zeros and poles, or actually poles of the system are on the left-hand side of the complex S-plane. I think you have already got through stability in analog systems on some of your electronics courses. Time shift invariance. So practically it means that system behavior does not depend on time, meaning the system remains constant in time. Again, time shift invariance is not a good or bad thing. A good example of not time shift invariant system is a parking meter. You are paying only for the from 7 a.m. to 6 p.m. in Helsinki region, I think. But, or is it 7 a.m. to 7 p.m.? That's when you pay, but then the system behavior changes at 7 p.m. You don't have to pay for the night parking in most regions of Helsinki. So practically time shift invariance is measured if the delay of output is the same as output for delayed signal. Okay. Next slide. How to actually describe a system mathematically? If the system is linear time shift invariance, so LTI system, that is the case for, say, most of the systems for this course, or yes, for the whole course. You don't want to have a non-causal system, or actually time shift variant system or non-linear system on this course yet. Those are more advanced topics. Then you can actually show that system behavior as this kind of difference equation. Where is my notation tool? So basically we have the two parts. That is the output part. Whoops. So the output, weighted output with delays. Okay, and the same thing for also the input. So practically all the linear time shift invariant system can be written in this form, and this is called the difference equation. Okay, that's the difference equation. Sometimes actually the difference equation is arranged in the next form, which gives you actually the calculation formula for the current output. So this one here on left is current output. Okay. Current output, and then basically we have the feed forward term, the first sum, bk x, x n minus k is the feed forward. Forward term, and the later one, look at the sign here. That's quite important to show, see the sign. Sign, since basically this is the red one and blue one here, exactly the same equation, only that the later one is taking the current output. So basically this is used to calculate the current output. Okay. And then the a, k, y, n minus k is the feedback term. Feedback of history. So history of output basically is fed into the system with some weights. Those weights actually, A and B, those are called the system coefficients. There we go. So, for example, for the difference equation of a 4-point running average filter, meaning that we are taking 4 subsequent samples of the input signal. So, okay, I'll note it again. So the first one here. Draw the first part, that's the current input signal. This one here is the previous one, so it basically is the history of the input. So we take 4 subsequent samples. Maybe I can actually draw that like that, and we have some oops. This is our system signal, okay, and then we take some samples out of it, for example here, there, there, there. So if this here is our x of n, yeah, x of n, for example x4, oops. Oh boy. Oh boy. Okay, so that's the x of n. X of n, for example, x of 4. To calculate the I of y of 4, we take this point and 3 previous ones. So these are taken into account when you are calculating the oops, text y of n, for example y of 4. Okay, so those are used to calculate the current value for output, and basically, yeah, that's the difference equation. Okay, you can also calculate the same value by the using the feedback, meaning the previous value. Would you take the previous value, which was a y of 3, you add the 1/4 of x of the current value, and you subtract the previous value, or the one which was basically used on the previous term. So that using the feedback, okay. There you go. So basically, using the feedback, calculating the same thing. What is the real difference? Actually, on 4-point running average filter, you don't need more than 2 additions, or actually 1 addition and 1 subtraction if you are using this feedback. Okay, so basically what I'm telling here is that the difference equation is just a formula to calculate the output. It is not unique. So that's where a block diagram actually comes as a helping tool. Block diagram is the implementation of the system using block symbols connected by arrows showing signal flow, just like in this picture. So this is the original feed forward system 4-point running average right here. Okay, pointer. So this one here. Running average, simply put by a block diagram, we have that 1/4 times x of n right here. So that's x of n, and here we have 1/4 of x of n. Then we have the, another delay here. So here I have x of n minus 1. Maybe I will start annotating again to get you into the right mood. Okay, so x of n, 1/4 of x of n is right here. Then at that point, we have the x of n minus 1 after this delay, and then at this point we have 1/4 times x of n minus 1. So practically this is quite simple to follow. If you have a block diagram, it's quite simple to follow what is the next, how this difference equation actually comes from the block diagram. Okay. Right, next. As you can see, we had here 4 multiplications. That's exactly the same as the difference equation on the beginning. Each of these terms are multiplied separately. This block diagram wastes resources. You know already that in microcontrollers, multiplication is a slower operation than addition, for example. So instead of this difference equation to calculate the output, this would be better since it has only 1 multiplication. This is something you would probably do in any case when you are doing the coding. So we just calculate the running sum and then multiply it by 1/4. actually this multiplication could also be here, either or, in here or in there. It still is one multiplication and 3 additions. It didn't do anything for the additions, number of additions, but this one does. Remember the previous slide, the feedback way of calculating it. Now we have the 1/4. Okay, so basically this is supposed to have the parentheses here. So 1/4 times x of n here minus 1/4 times x of n minus 4 right here, the negative input for the summation, and then you add the previous value of the output. The block diagram looks like that. Multiplication slower than addition. Simple logic. In modern processors, they usually go equally fast, but take any, say, 8-bit processor, the multiplication is slower because it basically does it. Let's see, if you do 8 by 8-bit multiplication, in any case, you need a 16-bit integer to save it. So that one already takes more time. But in addition to that, the logic part, how you multiply binary numbers together. In addition, you just add the bits and then add bits with carry flag. But on multiplication, you actually are doing each bit multiplication and adding those. That's the quick and dirty and silicon, the cheap on silicon version of doing multiplication. So practically, the integer multiplication is done in a loop. But, well, that's where the signal processors and signal processing blocks actually come in really handy, since with some extra silicon, you can do those multiplications equally fast. But even with the equally fast multiplications, on middle we have 1, 2, 3, 4 arithmetic operations. So all the additions and this multiplication, that's 4 the operations. On left hand side we have 7 arithmetic operations. On right hand side we have 2 arithmetic operations, or actually 3. 1, 2, 3, yes, 3 arithmetic operations. It's all about number of arithmetic operations. Okay, good. So block diagram, very useful for optimizing a system. Okay, block diagram can be used to determine a difference equation. So fundamentally, this is done quite easily. I'll take the annotation tool again. So you just need to follow the signal. So in this system, at that point, we have 0.5 times x of n. In this point here, we have x of n minus 1, since we have that one time shift delay right here at that point. In this point, we have x of n minus 2. Okay, and that here we have 0.5 times x of n minus 2 in this point. Here we have x of n minus 1. Okay, that is actually the x of n minus 1. At that point we have 0 minus, oh, it's plus, yes, 0.2 times y n minus 1. And then we have the addition. In this point, we have x of n minus 1, well, n, where does that come from? Plus 0.5 times xn minus 2 plus 0.2 times yn minus 1, which actually means that in here, y of n, I'll draw it here, y of n equals, maybe I'll do it different color, y of n equals, it comes from this summation, 0.5 x of n plus x of n minus 1 plus 0.5 times x of n minus 2 plus 0.2 y n minus 1. Ha! And that's the difference equation of the system, which comes directly from this point here. Oops. Red. Okay, so difference equation, a difference equation. Remember, there are several difference equations which are doing the same thing. The block diagram shows how to do it. The difference equation, or how to implement it. The difference equation gives a calculation formula. And if the difference equation is done from the optimized block diagram, then the difference equation is also the optimized formula how to calculate that the system. Okay, so that's how one of the exercises will be done today. Okay, so next one. Next up is the transfer function. Sorry, I need some water. So a transfer function, the same way as in analog domain, the transfer function actually describes the system in complex frequency domain. In continuous time, you actually have the Laplace transform. So you have the system transfer function is the same as the Laplace transform of output divided by Laplace transform of input. Okay, you remember that one probably from the some AC circuits classes you really like. On discrete time, we don't have the Laplace transform anymore, but the Z transform. But still the same thing. So we have the basically we have the output, Z transform of the output is same as the system transfer function times the input Z transform of input. So practically the same equation as in the for these analog systems, which are continuous time systems. So nothing new under the sun. The only thing is that we are dealing with sampled data, which means that we cannot use the Laplace transform anymore. But in any ways, the frequency domain is really handy to use, since instead of integrating of signal in time domain, you simply multiply it. So integral operation on time domain transfers into a multiplication operation on the complex frequency domain. So that's actually why Laplace and wait a minute. There are two guys, Laplace, and then Laplace was a mathematician, and then there was that one physicist. Was it Newton? Yeah, Newton has also two guys actually on are the inventors of integration. There's the Newton's method, and then there's the Laplace method. Laplace was a mathematician and made it beautiful theory how to integrate, while Newton's method actually is was, well, for a long time the Newton's method was how you calculate by numerically, to the numerical calculation routine. But anyways, the rest is history. The Laplace transform, the beauty of it simplifies integration by changing a lot of integrals into simple multiplications. Okay, that's history. Convolution. So basically, this one here, the convolution, in different means. Convolution. Z transform of system times Z transform of input. So actually, linear filtering is based on convolution. So this is how you do it on frequency domain. You have the Z transform of the system transfer function, which is, well, just the transfer function here, or input. Mumbling here. Sorry about that. And that is the Z transform of input, like that. And in frequency domain, it's a simple multiplication. So where do you need that convolution? Well, practically, the Z transform of calculating Z transform of a arbitrary signal, it's time consuming. So how do you eventually do the filtering is, let's see here, using the convolution. So you calculate a linear convolution, which is just simple sum, weighted sum of inputs. So the transfer function, the inverse Z transform of a transfer function is, where's my green? is impulse response. A simple signal in time, and if you convolute it with signal, you can calculate the current output. It's a weighted sum, so practically it's this quite similar to those the diagrams we already have, the block diagrams. Okay, I think our next slide probably is an example. Some properties, okay, I will just skip those. Transfer function is, Z transform is linear. There's a time shift property, and unit impulse and unit step actually have their own specific transfer functions. And here I have the 4-point running average filter. What does the transfer function look like? Well, eventually it comes like that using the properties. I'm not sure how much in detail I need to go with that one, but it follows fundamentally the same as in the in this continuous time zone. So you basically take the Z transform of the difference equation like that, then use the linearity property, meaning that if you have weighted sum, it is the same. You can take the one quarter out, so you can take that one outside and also break the terms. So it's a sum of 4 here. So you can break the terms into, for example, the first term here would be Z or 1 quarter. Oh boy, this is so much fun, of x of n. Like that, plus 1 quarter of the next one. Okay, which brings a formula like that, and remembering the definition, HZ, the transfer function is Z transform of output divided by Z transform of input. Directly just move this part in here. So divide both sides by this Z transform of x of n will actually bring you the last formula here. Okay. And remember the feedback way of calculations. So you can actually multiply and divide, or multiply by 1, meaning multiplying by 1 over z2 minus 1, divided by 1 over z2 minus 1. So that actually is 1. I'm not doing anything illegal, but if you do this one, the numerator polynomial actually will be 1 plus z2 minus 4, and then denominator will be 1 divided by z2 minus 1. Okay, and that's actually the feedback way of calculations. All right. Zeros and poles. So, transfer function of any LTI system is a rational polynomial of z, the same as the same way as the transfer function of analog system are rational polynomials of S. So nothing much changes here. And basically it means that if we are in a complex plane and we have, for example, second order polynomial, it has exactly two roots. Roots are the ones that actually where the either numerator or denominator polynomial goes to 0. And then we have the transfer function zeros, which are roots of the numerator polynomial. Then the upstairs of the division goes to 0, meaning that the transfer function is 0 on those special points. Poles are the ones, dangerous spots, so to speak, where basically the roots of denominator polynomial. If the transfer function goes to 0, it means that the transfer goes to infinity, which is quite meaningless value. Anyhow, since we have the second order, well, nth order polynomial, okay, so look at that one. We have nth order polynomial. The highest delay number of k is n. Okay, then we can actually also show it as the product. Shall I actually note it a little bit more here? So this form here is same as, okay, B0 times x of n plus P1 times x of n minus 1 plus B2 times x n minus 2 and so on. So that's the numerator. Oops. Denominator polynomial here is simply not x, z to minus 1. Oh boy. B0 z, so that's actually scalar times B1 z to the power of, can I actually, no, this is not, my notation tool is not good for that one. Okay, so maybe I have a better explanation on the next slide. Okay, but anyways, that's the summation term, and this is the multiplication. And we have the roots. Zeros and denominator polynomial special points are poles. By the way, we also have here a couple of other things like BK and AK. Okay, exactly the same coefficients as in difference equation. So linear time invariant system, you have the system coefficients, exactly the same system coefficients on difference equation and in transfer function there. Okay, so zeros and poles. The graphical representation of that zero pole plot, quite similar to the complex S-plane for analog systems, but now we are calling this zero pole plot as Argand's diagram, and it has some differences. The poles, pole points like that for a stable system, the poles are inside of the unit circle like that one. And this would be a fourth order system. So we have 4 zeros and 4 poles. And that's the highest delay also on the system. So it's fourth order and it has exactly 4 zeros and 4 poles, not more or less than that. And on the real Argand's diagram, there's also that common multiplier or scaling factor that's shown as the system amplification on the Argand's diagram. Usually it's not marked there since that's not a scaling term. What else? Yeah, well, the graphical representation, it's called zero pole plot. A little bit different from the S-plane. On S-plane, our signal was on imaginary axis. On the this Z-plane, the unit circle represents the signal with unity amplitude. Okay. Oh. Come on. Oh, yeah. There's some system gain. Oops. Okay, that's so unit circle actually is where Z is equal to e to j omega. Minus j omega. Okay, and multiple poles, real imaginary system gain. Yeah, nothing else. So calculating the 4-point running average filter of the zeros and poles. Okay, we can easily see that from calculating the zeros and poles from that one. We have this kind of polynomial actually which can be then divided into multiplication of polynomials. Z squared plus 1 multiplied by Z plus 1. So the Z plus 1 has a special point at 0. Maybe I will annotate again. Oops. All right. This polynomial has that one as a special point. Then that polynomial is 0 when Z squared is minus 1, which means J and minus J. And then we have the denominator polynomial has zeros, third degree zero at origin. There. All terms explained. Okay, the stability of the system. Earlier we talked about define the stability that for systems which has input, bounded input also would have bounded output. For that one, it requires that all poles are truly inside of the unit circle, meaning system like this, and it is about poles. Zeros can be anywhere. For example, this system is stable since the poles are inside of the unit circle.
Can I ask a question about this slide?
Yeah.
What is the omega?
Oh, omega. Yeah, good. Let me show you what is the omega. Omega is practically this angle here. That angle is omega. Omega is that angle. Okay, good. This one is also the stable system. The poles are inside of the unit circle. Again, zeros can be anywhere. Okay. Any poles are outside, then the system is unstable. And if there are poles on the inside and on the unit circle, so in case we have a pole, for example, exactly at some certain location here, that's critically stable, which means that it's a oscillator. And again, zeros can be anywhere, inside, outside, or on the unit circle. Good. So that's about zeros and poles. Transfer functions. This actually belongs into the section of transfer functions. The transfer functions are really practical too when we are playing with blocks, meaning when we are combining blocks. Okay, by the way, that combination here is kind of funny. I noticed that something is missing here. Or maybe I should actually put a... Okay, so that's actually add block here. Yeah, so not shorting the wires, but adding the wires together. So if we have parallel systems, so one system and another system, and we want to actually combine these systems, then we can represent it simply by one single system which has the both system transfer functions added together. Simple operation. So remember the linearity property of the transfer function. It's linear if the system is linear, and that means that you can then do addition either separate systems or a system put together. Sometimes it is better to break out a system to smaller parallel systems. For example, to speed up the process in multiple processor system. So you calculate the output of the system in 2 different processors and then add these results together. Sometimes it might be actually faster to do it like that. Not always, but sometimes. Cascaded systems, meaning in series, means that you have the input for the full system here, and you have a combined system. Again, or if you have cascaded systems or series systems, you just multiply these transfer functions together. Simple. Parallel, meaning adding. Cascaded, meaning you multiply the transfer functions. Similar to the analog systems. For example, if you have 2 filters, you can either have 2 separate blocks to do this, the filtering, or then you can also use a combined system. Usually it's such that you will design it as a combined system, and then you implement the filter in second order blocks. On analog filter design, with one single operational amplifier, you can do that Sallen key filter, which is second order filter. So in order to make higher order filters, you cascade these blocks, and each of those have their own second order transfer function. Okay. Oops, I have annotation tool still on. Clear. Since these transfer functions are also linear, then you can also move the summation either before or after. You just need to basically, if you move this transfer function on the left-hand side, then of course you need to put that block right on the left-hand side here on both of these the inputs, and it's the same as that one. Yeah, simple. So in reality, if you have feeding in 2 signals on the same system, I would guess this would be the more efficient way of doing it. You add the signals together and then feed it into one system. Anyhow, this kind of playing, it is done to optimize this total transfer function for calculation. So remember, we are optimizing the implementation to have as little on the number of operations as possible. Okay, sometimes you need to move the transfer function after a summation. Mathematically, it means that you basically then move it on the other side, and then to the other brand, you have basically GC divided by GC here, which is transfer function 1. When you move that GC term, then basically what is remaining is the 1 over GC. So you have the inverse system here, which, okay, a warning about that one. This brand actually might become very unstable. And in reality, if you do it on a implementation, then you have a very unstable input for summation. You never know what happens here. For example, you can have the arithmetic overflow, and then the rest of that one is garbage. But anyways, for mathematically, that is really true, and it is used for optimizing, for example, some control loops or something like that. Very complex systems. Okay. Loop reduction. Interesting. Yeah. So actually, if you analyze this one, here you have x of z, this is y of z. You can actually see that, maybe I should annotate to see if I can still do it by hand. So text input x of z, oops, and output is y of z, which here is actually same as g of z, but on the other hand, you get target times whatever comes on from the left hand side is x of z minus h of z times g of z. Maybe it actually becomes, oops. Okay, yeah, but anyways. So practically this loop reduced as a single transfer function looks like that. It's simple mathematics, remembering that in a system, if you have a transfer function in a loop, transfer function in a loop, or transfer function anywhere, you are dealing with a z-transformed signals on. All right, so practically in, okay, I'll do it again. So if we have x of z as input, there in this point we have h of z times y of z. Okay, we have transfer functions. So any of these blocks will actually just, whatever is the input, the output is the transfer function times the input. And here we have the y of z, which is the output. Okay. Here we have h of z times y of z. Okay, now I got it. G of z times whatever we have on the input is x of z minus y of z times h of z times that one. Yes, like this. And if you there calculate what is y of z divided by x of z, which is a transfer function of the whole block. You will get that one. Okay, so useful for loop reduction, especially on the say control systems, or if you have a more complex system which you always have some feedback loops. The last picture here, multiple input but still single output. If we have a linear system, then if we want to evaluate, for example, what is the effect of an external load to a system, that block diagram actually is a classic single loop control system, where on the control system point of view, let me mark again something here. This one is the plant. I hope you have watched the video made by MathWorks. Anssi Ikonen put that link into the workspace. What is a simple control system? So there's a plant that we want to operate. For example, electric motor, or actually a robot which moves, which has an electric motor, so it's the whole system. It has some sort of transfer function, meaning that it describes how slowly it reacts for the input. Usually, the control block is divided in two parts: the amplifier part and control. So control signal just gives the say some bounded values, for example, between 1 and -1 values for the amplifier. Amplifier is the real thing which has the transistors to drive the high current. And of course, it also has some transfer function. Usually it operates as a low-pass filter, or if the plant actually requires a PWM signal, then this amplifier part would be the PWM driver. Control signal is something that controls that output, which goes directly to the plant. Okay. This is the value we want to set, control value, and here is a measurement. For example, if plant tries to increase the speed up to, say, 1000 RPM or some RPM, this would be your tachometer signal, and this feedback measures directly to whatever we want to control. So we are measuring whatever we want to control, and that one is the difference signal. And this feedback loop, if it's done correctly, then tries to minimize the error, meaning the difference between the RPM value, what we want, and the controllable value, what is real. Okay, so that's a simple controlling loop, which yet tries to minimize the error. Same as the negative feedback on operational amplifier. The operational amplifier with a negative feedback has nothing else to do than try to keep that error between, or difference between the inputs as small as possible. Okay, same thing here. This loop should be trying to set up the error signal so that these these are actually the control signals, so that it minimizes the difference between wanted value and the actual value. Okay, that's a simple control loop. And here we have the external load or external error source. For example, you have a control loop and you want to know if you have found this steady state solution, you want to know what happens if you push the system a little bit externally. For example, if you have that motor control that tries to run a motor at 500 RPM, then you put a load into it. For example, you are driving a car and you are going uphill, starting to going uphill. This control loop actually should react for the external error and try to minimize the error again. So practically on this kind of multiple input systems are useful when you are trying to or when you are designing this system against external changes. So there you can then calculate the transfer function where this one is our y of c and this one is our x of c. So transfer function for external errors. Okay. And it happens the same way as, deriving any transfer functions. Okay, that was a 1.5 hours full of information again. Now we have a 15-minute break again, and we will be back unless you have any questions, of course. If you have questions, just write on the chat or chat window, or you can also talk if you wish. If anything was totally unclear. I'm trying to give more, say, practical tools for you, again, on that method, on that Octave laboratory session. So then we can take a look how this one actually is done in Octave, meaning some tool, and then later on you will get also tools to how to implement that one on your microcontroller environment, I hope. Now, do you know when DSP E1 is being evaluated? I try to evaluate this first exercise during the weekend. So I know the Friday is not a good day for having the deadlines. If it was Thursday deadline, then I might have a chance of giving you the feedback immediately before this starts. But okay, but you also need some time to do the exercises. So during the weekend, any other questions? Okay, if not, then also we have a break coming back at 12:45. Okay.